All right. So earlier when we began talking about limits, I told you that the definition that I gave you for limits was not the formal definition of a limit. And the definition that I gave you for limits, while works for all of the purposes of this particular class, sometimes it's a little bit a little bit big. So what do I mean by that? In the definition that I gave you earlier, the believe went like this. It went like, you know, the limit of x goes to a of f of x equals L if f of x is arbitrarily close to L for all x consistently close to A. So that's the definition, and this is the not equal to. That's the definition that we introduced early on, in lecture 4 of the limit. So we began analyzing the limit analytically. Now this definition, for our purposes, it's okay, it will work. But these two words are arbitrarily close or arbitrarily large that we've been using throughout, and sufficiently close, sufficiently fast, they bring some issues when we are actually trying to prove why these things feel the case. Because they're very big. What do we mean by sufficiently close or arbitrarily close or arbitrarily large? So there actually is more to actually make this definition precise and make it accurate. So first, number one, making f of x arbitrarily close to L means that the distance between f of x and L is made small. Talking about distances here. In particular, the distance between f of x and L can be expressed as the absolute value of f of x minus L. Right, so this is how we describe distances by using the absolute value. Two, similarly, to make f sufficiently close to A means that the distance between x and A can be made small. And we write that out, we express it out the absolute value of x minus A. Okay, so for the purposes of our class, we will not be using this definition that I'm going to write now for find the limits, and I'm going to 2's, while this is the case. However, you are free to look up the 2's and while this is the case on your own. The book for our class, the back has the 2's of this. But the proof of this is beyond the scope of this class, that's for sure. So it is important that you at least see the definition, the proper definition of, of the limit of a function. This what sometimes is also called the delta epsilon definition. So if you were to Google delta epsilon definition of a function, this is what you will probably see. You will say assume f of x is defined for all x the sum of an integer containing x except possibly x. Okay, so we say f of x, so the limit of f of x, so the limit of f of x as x approaches a, this is the definition of a limit, which is good enough. Limit x goes to a if f of x equals x. So this is so far very similar to the definition that we had written before. Now, one of the main differences is the fact that we are not using the word arbitrarily large or arbitrarily close or sufficiently close or small. Now, this is where the definition is actually different, because now we're actually going to introduce that notion of being arbitrarily close or far. And my apologies, I brought this up, but I need to look at the master. All right. So what is the rest of the definition? Is if for any, and the next letter that I'm going to write is the Greek letter epsilon. So epsilon, it looks like an E, greater than 0, there exists delta, so that's the way that I write delta, greater than 0, and both of these are numbers, delta and epsilon are numbers, such that the distance between f of x and the limit L is less than epsilon whenever the distance between x and a is less than delta. So this is where the definitions of the limit of functions differ. The fact that we are now explicitly stating the fact that for any epsilon, for any number, any real number bigger than 0, there exists at least one delta that's also bigger than 0, that's positive, such that the distance between the output values of the function and the limit of the function can be made, that distance can be made less than the number epsilon that you choose whenever x is very close to a, and that distance, while positive, is a positive distance, is less than delta. So there's a lot to unpack here. This is an existence theorem, so it means that there must exist one delta such that this is true. Now, if you are doing a problem using the delta epsilon definition of a limit, then you have to actually figure out what epsilon and delta are. That's most that's most of the work, actually, just figuring out what this delta and this epsilon are. Let me just give you a graphical example really quickly. Let's say you're dealing with some function, and this function you're interested in looking at it between the intervals 1 and 2. So the function kind of goes up like this, right? Let's say here we have 2. Let's say here we have 4. So 3 or somewhere over here. So if you were looking at the limit of this particular function as x goes to 2, so as x goes here, then the way that the delta epsilon definition works is that what you're trying to do is you're taking this portion right here. This is the distance that you're making close to 2. And let's say we choose delta to be 1. So what you're saying is that this distance, this x minus 2, is less than 1. You can make it less than 1, but it still is a positive number. So it's a decimal number, let's say. So you're going to make this distance very small. And when that happens, you make the function values also be less than, let's say, the number 1. So what's happening here is that you're trapping your function, and you're looking at this rectangle that I have here. And if you continue to make this distance smaller and smaller, let's say instead of picking 1, you now pick I don't know, let's say you pick 0.3333, and it goes on, right? Then that means that if somebody gave you an epsilon, they don't have to be the same numbers. If somebody gave you this epsilon, now you want to make this distance even smaller. So that just means that instead of being 1 unit away, so this is 1 unit away, now you're gonna be a third away. So now you're gonna be between here and here on that axis, and now between here and here on this axis. So now you're looking at the neighborhood that's in green. But let's say somebody told you, hey, I want epsilon to be even smaller than a third. So let's say somebody told you, okay, make epsilon be 0.01. Well, that means that now we're interested in making f of x minus 3, that distance, be less than 0.01. So that means that now we're looking at values very, very close, to 3 on the y-axis. And because of the theorem, for the limit to exist, then we need to find a delta, one delta, such that that's the case. So let's say we found that delta, and that delta also happens to be 0.01. That means that now we're looking at this interval around 2. Remember, we're making these distances very small, so we're getting actually closer to the 2 and closer to the 3. So that means that we're looking now at this image right there. Now, what if you were given another function? If you were given another function like let's say you're given 6x squared plus 12x minus 5. If you're given a function like this and you're told to find this limit as x goes to 3, let's say this is f of x, and you actually know what the limit is. So let's say, if you compute this, that will be 6 times 9 plus 12 times 3 minus 5. So if you were to compute this, that's going to give you some number. I'll call it C, because I'm too lazy to actually look it up. Then what you need to do is you need to find an epsilon So you need to find an epsilon such that, this is supposed to be a question mark, you need to find an epsilon such that this distance, f of x minus 3, not minus 3, f of x minus c, the value, the limit, is less than that epsilon. And then you need to also find out what this distance has to be, this delta has to be, for this to be the case. So you need to find the delta for the given epsilon. So this is the so-called delta epsilon definition of a limit. Like I said, it becomes very important whenever you're dealing with other theorems in other classes, and even in this class. Like later in this, if you were to take Calc 2 or even Calc 3, you will encounter more theorems where the delta epsilon definition of the limit is used to prove the theorems that are given. So I just wanted to mention that in passing, because it is very important that you at least see it once. You see the delta epsilon definition of a limit at least once. Thank you for your time.